So far, we've looked at the direct perception model, which allows for highway driving. But how can we transfer this idea to cities? Well, given that we know already how we can transfer imitation learning to driving intersections by considering an additional directional navigation command as an input, we can utilize the same idea, of course, to transfer the idea of direct perception to make it applicable also to inner city driving. This is a model that my group has proposed at CARLA 2018. It's called Conditional Affordance Learning for Driving in Urban Environments, borrowing the terminology of conditional imitation learning, but in this case we have a neural network that doesn't directly predict the control commands, but it predicts low-dimensional affordances, just like the direct perception model that we've seen before. The only difference here is now that in addition to the images, this model also takes the directional input, the navigational command provided by the high-level GPS system that tells the model at the next intersection go left or at the next intersection go straight as additional input. We considered the CARLA Simulator for developing and testing this model. We've already seen the CARLA Simulator. In the CARLA Simulator, the goal is to drive from a starting location to an end location as fast, safely, and comfortably as possible. And there's different levels of difficulty. The simplest level is to go just straight. The next one is to make one turn, and then the final one in this original CARLA Simulator 0.84 is to make multiple turns in order to reach the target location. And the CARLA Simulator also counts the infractions that occur. And of course, we want to build an agent that produces as little infractions as possible. And infractions in CARLA are counted by driving on the wrong lane, for example, or driving on the sidewalk, running a red light, by violating the speed limit, colliding with other vehicles, or hitting other objects. Therefore, our goal, of course, is to go from A to B without doing any or with doing as little as possible of these infractions here. And the question now is, which affordances do we need to implement such a driving behavior? In our conditional affordance learning approach, we utilized only 6 different affordances. We used the distance to the center line and the relative angle to the road in order to implement a steering controller. These 2 things are almost always needed in order to safely and comfortably steer the vehicle to the center of the road. You need to know how far are you from the center line. The center line is in the middle of the road. And so this is the translation, the lateral translation in this direction here with respect to the center line. And you of course need also to know what is the orientation of the vehicle with respect to that center line. Are we already aligned with the center line, or do we need to steer towards the center line in order to be aligned with the center line? And we want to minimize both to 0. We want to have as little distance to the center line as possible, and we want to have the relative angle to the road to be 0 in order to be aligned with the lane. Another affordance that we use, similar to the direct perception paper, is the distance to the lead vehicle, the distance to the vehicle in the same lane. Furthermore, we use speed signs, traffic lights, and hazard stops as additional affordances, where for speed signs we predict the speed limit, the actual speed limit that has been observed by recognizing the speed sign. And for traffic lights, we only predict if there's a traffic light in front of us, directly in front of us so that it's relevant for us, and if that traffic light is red or not. Because of course we only need to slow down if there is a traffic light that's relevant to us right in front of us, and if that traffic light is red. And in addition, we have this hazard stop affordance, which is just a binary value that tells us, well, there is something on the road. You have to brake now, otherwise you will hit that obstacle on the road. And an example is given here, where a pedestrian crosses the road. That happens frequently in CARLA. And here on the right also, when we come close to another car where we have to stop, and maybe we got too close to that car, so we have to immediately hit the brake. These are the only 6 values that we predict. We have a 6-dimensional, a very low dimensional space that's then input to the controller. Here are the affordances again. The distance to the center line, which is this distance here. The relative angle to the road, which is this angle here. The distance to the lead vehicle, which is not shown but measured here as 15 meters. And the speed signs, the traffic lights, and the hazard, the potential hazard in front of us. Now, in order to generate a data set that comprises both input images and the ground truth affordances, we can run our simulation, because everything happens here in simulation. In reality, we would have to annotate these affordances, but in this case, the simulator directly provides them to us, so we don't need to annotate them. But the question is, how do we obtain these affordances from the simulator while driving around in that simulation? And what we did in this paper is very simple. So we basically just defined, the distance to the center line and the relative angle to the road can be directly measured. They are directly available from the simulator because we know exactly the map, and we know the state of the eco vehicle, so we can measure these. But for the distance to the lead vehicle, the speed signs, traffic lights, and hazard stops, we implemented certain regions of attention in bird's eye view. Again, we have the full state from the simulator at training time. And now, given these regions that are defined ad hoc in a heuristic fashion, we simply check other vehicles, for example, that are inside, in this case A3, which are potential lead vehicles, and then we take the closest one and return this as the affordance for that vehicle in order to generate the training data that our network has to predict. Similarly, we have a smaller box to predict hazards, and if another object, a car or a pedestrian, enters that box, we predict the hazard affordance. Or we set the ground truth hazard affordance to 1. That needs to be predicted by the perception network. Similarly, for traffic signs, for speed signs, we have a box here, and for traffic lights that retrieves from the simulator if there's a traffic light or a speed sign inside that box and what the relevant speed limit is of that speed sign. And this is what we use as affordance. So this is how the training data is generated. But of course, at test time, this is unavailable. At test time, the only input that the model sees is the images and the directional command, the high-level navigational command provided by the GPS system. And based on that, it has to predict the affordances. And based on the affordances, the controller has to provide the control commands to the vehicle. This is illustrated here. In the bottom, in the dashed box, we see the CARLA Simulator, which simulates the environment with the agent and also provides the high-level navigational command that tells us at the next intersection, take a left turn, for example. And it provides also the image, which is the state or the observation that is input to the conditional affordance learning agent here on the top. The conditional affordance learning agent then takes this image, extracts features from that image, actually uses multiple images over time, extracts features from a number of recent images, a history of recent images, and puts these features into a memory. And this memory is then accessed by the task blocks with a multi-layer perceptron that predicts the affordances. And as you can see, some of the task blocks are unconditional and some are conditional. For example, the hazard stop is unconditional because it doesn't depend on the navigational command if we should stop or not. If there's something in front of us, we should just stop no matter what. But for example, the relative angle to the road heavily depends on the navigational command. If we are on an intersection, this relative angle will change depending on if the vehicle has to go left or right, etc. So that's the reason why some of these task blocks here are unconditional and some are conditional. The output of this perception module is then 6 affordance indicators that are fed into the controller that provides the control commands. What does the controller look like? The longitudinal control is a simple finite state machine combined with a PID controller for cruising and a car following model, similar to the one we've seen before. The finite state machine is illustrated here with the affordances coming into the controller from the left, and it has states that are sorted based on priority. So for example, if the hazard stop flag is true, if the hazard stop has been predicted by the perception module, we do a full brake and we don't care about any of the other states here. If there's no hazard stop but there's a red light, we try to come to a stop in front of the red light. If neither the hazard stop nor the red light have been detected, but we are over the speed limit, we're trying to reduce the speed of the vehicle to follow the speed limit that currently holds. And if neither of these three are present, then we are in the car following or the cruising mode. Cruising means there's no car in front of us. Car following means we keep a distance of, say, up to 35 behind the preceding vehicle. And cruising means we just go at maximal allowed speed because there's nothing in front of us. As lateral controller, we implemented the so-called Stanley controller that has steered the Stanley vehicle, Stanford's winning entry to the DARPA Urban Challenge, or the DARPA Grand Challenge. And it also is composed of multiple terms similar to the controller we've seen before. It has a relative steering term and a cross-track error term, and also a damping term to avoid oscillations. And we're going to talk about this controller in more detail in later lectures where we talk about controllers. So how can we now learn the parameters of this model, the parameters of the perception stack? Well, we implemented a multitask model where we have a common backbone such that there's only a single forward pass with multiple shallow heads implemented, which leads to fast learning and inference. The dataset that we use is comprising random driving using the controller that I've just shown operating on the ground truth affordances. We have a simulator, so we can just use the ground truth affordances in order to drive safely through that environment in order to generate the data. Overall, we used 240,000 images with ground truth affordances to learn the perception stack. The loss function are standard loss functions. For example, for the discrete affordances, we use a standard cross-entropy error, and for the continuous affordances, we use the mean average error. However, because the discrete affordances, for example, are so unbalanced, for example, a hazard occurs only once in a while, we use a class reweighting here in order to pay more emphasis on the actual relevant scenarios. And this is then optimized with Adam using a batch size of 32. And to adjust the controller, the PID controller, we use standard procedures, which we'll talk about also in later lectures. For example, the Ziegler-Nichols procedure in order to set up the parameters of the controller. The data, as already mentioned, is collected based on navigation, based on the true affordances. And at each intersection, we provide a random navigational command as input to steer the vehicle into a random direction at the next intersection. This high-level command. It's important, as always, in deep learning to use a lot of data augmentation, and we use, well, we don't use image flipping because that would change right-hand driving to left-hand driving. So that's not plausible, but we use color, contrast, and brightness changes and add Gaussian noise. And also we provoke rear-end collisions, because if the model has never seen such collisions, if it never has seen hazards, it will not be able to predict hazards well. And then we also use camera pose randomization and adjusting the affordances appropriately. So whenever we record, we move the camera and we also reorient the camera to get more data from slightly different angles than the position that we are actually currently driving on. Here are some results. This is a big table. You don't have to look at all the numbers, but what's important here is that in particular when generalizing to unseen towns and unseen weather conditions, this proposed model in this CARLA 0.84 benchmark leads to significantly more robust driving behavior. These are success rates here, and you can see that the conditional imitation learning approach or a reinforcement learning approach really have difficulties to generalize to new towns and new weather situations when we have other dynamic vehicles and pedestrians on the road, and we have to drive courses with multiple turns, which are the last two rows in this table. The first two are the simpler scenarios. Okay. And finally, I want to show you some results of how this driving looks like. So the first is just a conditional navigation. Based on the conditional high-level navigation command, using the conditional affordance learning model, we're navigating in this CARLA environment. You can see the vehicle pays attention to traffic lights and does the turn that is input by the high-level navigation command. What you can see here on the left is not the image that the agent receives, but this is an overhead view. The image that the agent receives is from within, is from the camera that's within the vehicle, of course. So it's even a slightly more difficult perspective. You can see that the environment provides all kinds of challenges, many red lights, many junctions, and also puddles on the road that can be misled or can mislead the vehicle to drive or to misinterpret them as lane markings, for example. Okay, so let's look at another example. This is a video that illustrates the behavior with respect to speed limits. So in this case, the speed signs are, the agent recognizes the speed signs. And then in this case here, we are going to maximum speed because the speed limit here is 90 kilometers per hour. And then shortly before the turn, the speed limit lowers to 30 kilometers per hour. So the vehicle brakes abruptly. And then now the speed limit, here the ground truth is in green here, is again going up to 60 kilometers, 90 kilometers per hour. And so the vehicle accelerates again. So the current speed is in blue here, and you can see these little jumps here because there's actually a model for the gear shift implemented, so the vehicle has to shift gears. Here is an example of car following. There's a car in front of us, and what is displayed here in the plot on the right is the ground truth distance to the vehicle in front of us and the predicted distance by the neural network. And of course, that's a very hard task because from the perspective of the camera, there's no distance sensor implemented. It's just an RGB image. And so it's hard to predict precisely how far a vehicle is in front of us. But as you can see on average, the prediction is doing quite well, and it allows the vehicle to brake when the preceding vehicle in front of us brakes, in order to come to a stop and not crash into that vehicle. Here's an example of a hazard occurring. There will be a pedestrian that enters the road, and the hazard indicator is predicted by the perception stack. And so the vehicle comes to a full stop before continuing its drive. What we can also do is we can visualize where the perception stack pays attention to. And we do this here in this case using a technique that's called GradCam, that's similar to what we've discussed in the previous lecture. Basically backpropagates gradients in order to figure out which regions of the image are relevant for a particular decision. And what's interesting here is that the vehicle indeed pays attention, or the perception stack pays attention to regions where other hazards could potentially emerge, and also the traffic light. And what's interesting now is that as soon as the pedestrian is entering the road, the attention fully focuses on the pedestrian, despite the fact that the pedestrian is actually not fully visible yet, but we see mostly the shadow and parts of the pedestrian. But then once the pedestrian has actually entered our lane, all the attention of the model is focused on the pedestrian until the pedestrian has left our lane and the hazard has gone. Here's an example where we can see how attention is focused towards a red light. Now the light switches to red, and the attention is all on that red light in order to detect when the vehicle can safely accelerate again. In this case, we looked at the path planning capabilities of the model. Of course, there is no explicit path planning module here. We just have the perception stack that predicts the affordances that are used for control. So all the planning is implicit. But what we can see here is the trajectory that has been taken by the vehicle in red and the optimal trajectory that the vehicle was supposed to take in green. And you can see that the trajectory, while not leading to any infraction, has been influenced by the rain and the puddles on the road. The vehicle was misinterpreting these as the lane markings and was following actually the dry part of the road rather than taking the turn more directly. This is another way of visualizing for self-driving agents what has happened. Let's also have a look at some failure cases. So in this case, the sun is very low and leads to a lens flare on the image, which is also simulated by the CARLA environment. And in this case, the vehicle has stopped because it misinterpreted this lens flare as a obstacle, a pedestrian or a vehicle on the road. Here's another failure case. In this case, we're looking at a false negative, which means that there is a hazard on the road, but the vehicle has not yet detected that hazard. And this problem here is because that pedestrian has just entered our lane, but it hasn't fully entered our lane. In the next few frames, the hazard would have been detected by the vehicle, but because the bounding box that has been chosen, remember this bird's eye view bounding box that I've showed before, in order to generate the ground truth affordances was smaller than the lane, this hazard hasn't been detected yet. And in this case, the hazard has been detected, but the red light has also been detected, despite the fact that the red light is further away than relevant for braking. It's actually quite difficult from a single image to detect the size of a car in front of us and therefore the distance, because the size is the only cue that we can measure the distance to an object. And similarly for traffic lights, it's very hard to measure the exact distance to the traffic light. And so sometimes it happens when you do driving just based on visual inputs that the distances are not quite right, and so the vehicle, for example, stops too early.